This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
Good evening. My name is Cheryl Peach. I'm a program scientist here at the Birch Aquarium at Scripps. Would like to welcome you to the Jeffrey B. Graham Perspectives on Ocean Science lecture series. It's a great pleasure this evening to have Dr. Yuri Fialko here as our speaker. Yuri is a professor of geophysics here at Scripps in the Institute of Geophysics and Planetary Physics. He came here in 2001, I believe, after doing his PhD at Princeton in geophysics and a postdoctoral appointment at California Institute of Technology in seismology. Yuri is actually a recipient of a very prestigious award from NSF. It's called the Career Award. It's given to outstanding young scientists for excellence in both research and education, near and dear to my heart, so that's why I included it in the introduction. Yuri's active in many areas related to seismology and geophysics, including looking at earthquakes in Southern California. That's one of the topics for this evening. He's also involved with a national program looking at applying modern observational, analytical, and telecommunications technologies to look at the structure and evolution of the Earth's crust. So he's looking at deformation at the sub-centimeter scale related to earthquakes and other deformation processes. So I hope you'll join me in welcoming Yuri this evening for his talk titled Earthquakes in Southern California, A View from Space. Yuri, thank you very much.
All right, well, thank you very much for a generous introduction, and thank you all for coming. It's my great pleasure to have this opportunity to talk to you about some of the work that we're doing at Scripps. What I would like to discuss today is the use of space geodesy for studying earthquakes in California and beyond. I would also be talking about the broader tectonic context in which we have seismicity in California, and speculate in the end about what future may have in store for us and how we can and should prepare for it. The work that I will be presenting is not just my own research. I will be also showing work from other people, both here at Scripps and elsewhere, as well as some very gifted graduate students and postdocs. So many of you may have noticed that this year we had quite a few of notable earthquakes in this hemisphere, starting with magnitude 7.0 earthquake that struck Haiti in January of this year. This happened to be truly a humanitarian catastrophe with a death count in the range of hundreds of thousands and very dramatic impacts on the local economy. Now Haiti is slowly rebuilding with the help of international community, but things are still incredibly tough over there. Then in February of this year, we had a great magnitude 8.8 earthquake that shook most of Chile. There was a widespread damage to the infrastructure that one might expect based on the earthquake of this size, but fortunately the loss of life was much, much smaller than Haiti, and the lesson there is that seismic building codes and the proper reinforcement of those codes really do save lives and pay off. Then in April, on Easter Sunday, we had an earthquake in northern Baja California that many of you may have felt if you were in town. This earthquake caused some widespread damage, but claimed only 2 lives. We'll come back and discuss this earthquake in further detail. But for now, let me just point out that I was plotting the locations of these earthquakes on this so-called global seismic hazard map that shows the probability of exceedance of ground acceleration of a certain magnitude over a certain period of time, in this case 50 years. And the point that I'd like to make here is that these earthquakes all happened in areas of red, where we knew there is a pretty good chance that a significant earthquake would happen. So the point that I'd like to make is that we are not doing too bad in terms of long-term forecasts of significant seismicity, and none of these events were surprises for the scientific community in terms of where they happened and how large they were. Just to bring this point a little bit closer to home, this is a similar map of earthquake probabilities for the state of California, in which colors show the likelihood that somewhere in this area there will be an earthquake larger than magnitude 7.6 Northridge earthquake that happened in the LA area in 1994. So warmer color indicates larger probability of a significant earthquake. And it's not really a question if a major earthquake will strike Southern California, but when and where. As you can see on this map, the highest probability, the highest estimated probability anywhere in the state is associated with the southernmost part of the San Andreas Fault, which has about 59% chance of an earthquake of this magnitude happening over the next 30 years. So what I'm going to do is that I will talk about some science that goes beyond these estimates and then also discuss some of the local hazards we have in our own backyard. Well, first let me step back and discuss why we have earthquakes in California in general. As most of you know, California hosts a major boundary between two tectonic plates, the North American plate and Pacific plate, and it's the relative motion between these two plates is what's causing stress increase in the crust and eventual yielding that generates earthquakes. We all know that Southern California is earthquake country. In fact, there are over 30 earthquakes that are happening every day in California, and this map shows large earthquakes that happen over the last century, shown by these color circles, and smaller earthquakes with magnitude less than 4, shown by these small dots, and those are the little earthquakes that are happening on an everyday basis. So earthquakes are a fact of life in California, and local public is generally very knowledgeable about earthquake and seismicity in general. Of course, there are some extreme views. On one hand, we have people that have, how should I put it, a bit of a cavalier attitude, like been there, we've seen them all, there is nothing that can happen that we haven't already experienced. This kind of attitude is, has propagated into the popular culture and is perhaps best illustrated by an episode from one of my favorite movies, The LA Story.
Sarah, what do you do?
I'm here writing an article about Los Angeles for the London Times.
Well, you've come to the right place.
What do you do for a living, Raleigh?
Yeah. I deal in English paintings.
Abstract or realistic?
Depends on which way you look at them, I suppose.
What's this?
An earthquake. How strong is it, Harris? I give it a 4.
Try to get like 5 or maybe 10.
So, when an executive or a business person...
All right, on the other extreme, we have a more of an apocalyptic view of some kind of a doomsday scenario in which there may be a magnitude 10.5 earthquake that would cause much of California falling into the ocean. These are some animations of this kind of scenario. I guess some people just like the general notion that SeaWorld can extend all the way into the downtown of San Diego. So what does science tell us about what's possible and what's impossible? This is an illustration of our current understanding of how major mature strike slip faults like the San Andreas Fault operate from an earthquake to an earthquake. Down at greater depths, where pressures and temperatures are high enough so that earthquakes cannot really support significant stress and they cannot fail in a brittle fashion. And so what rocks do is that they simply creep at a constant rate, accommodating this steady plate motion. This creep at greater depths puts stress in the upper crust, which bends and flexes in response. And this also increases stress on the shallow portion of the fault. And when that stress reaches a certain value, at some point, rupture happens, and it produces seismic waves, and the shallow crust then catches up with the deeper layers below it. And so the process then repeats, and over multiple earthquake cycles on timescales of thousands to millions of years, the total combined motion from these two types of interseismic and coseismic deformation will sum up to something that looks like a rigid block motion of two plates past one another. Well, the twist to the story is that major faults don't break at once. They tend to break in individual segments. And so when one segment breaks, it puts stress on the neighboring segment. And then that segment would eventually fail. And so this is how motion is accommodated over a long period of time. This kind of model is well illustrated if we look at the historic seismicity over the San Andreas fault system. This is a map in which ruptures were color-coded according to their time. And if we just go forward in time, the last time the central section of San Andreas broke in a major earthquake was in 1857. This was the Great Fort Tejon earthquake. Then going further in time, now this was the rupture that produced the Great San Francisco earthquake in 1906. The central and northern section of San Andreas are separated by this so-called creeping section of the fault, in which the two fault sides are just sliding past one another at a constant rate, and they do not accumulate much stress, and therefore they do not pose a significant seismic hazard. Fast forwarding through time all the way to now, one thing that you may notice is that the only section of the fault that hasn't ruptured in historic times is this section at the very south. And studies of paleoseismology using geologic methods in fact indicated that this part of the fault did produce large earthquakes in the past, and that's a sure indication that it will break again in the future. So even though there were not major earthquake on the San Andreas itself in the southern section in historic times, there were sure plenty of large earthquakes happening around the fault. And in fact, over the last 50 years, Southern California was the most seismically active part of the western United States. Here are some examples of major earthquakes that were happening in recent years. This pair of earthquakes, the Landers and Hector Minor earthquake of magnitude greater than 7, fortunately happened in the remote Mojave Desert part of the state, and therefore they did not cause much of a damage. The 1994 Northridge earthquake was the largest and the costliest natural disaster in the US history up until Hurricane Katrina hit. And that earthquake wasn't even that great. It was only magnitude 7.6. And then last April we had El Mayor earthquake at the US-Mexico border. What does this pattern of activity really mean? We're not sure, but it offers somewhat uncomfortable analogy with the activity that was happening on the northern section of the fault around San Francisco. Again, just to remind ourselves, this is the northern section that broke in the 1906 event, shown here by red, and this is some of the aftermath of the San Francisco earthquake. And if we look at the seismicity around the fault in years preceding the 1906 event, the pattern is shown here in this figure. So here we have time axis along this line, and each box here shows a significant earthquake with the respective magnitude. The records were not that good before year 1850 because there were not enough people living in the state, in that part of the state at that time. But we have a pretty good knowledge of the number of earthquakes that were happening in the 50 years before 1906 event, and it looked like crust was responding to some significant loading. So it was as if the crust was being loaded to some critical level, leading up to the magnitude 8 earthquake, and after it happened, it is effectively shut down seismicity for almost 50 years, and now it starts to pick up again in the Bay Area. All right, so what can we do to better understand earthquakes and the slow tectonic deformation that is causing them? Well, one thing that we can do is measured deformation at the Earth's surface, both from earthquakes and slow tectonic loading, and then relate the deformation to the accumulation of stress at greater depths. So now let me introduce some of the observation tools that we're using for this purpose. First, we'll rely on the GPS, or Global Positioning System, to measure velocities or displacements at select points on the ground that have pre-established monuments. The way GPS works is that we have a constellation of 24 satellites that are constantly orbiting, and these satellites are equipped with highly precise atomic clocks and time beacons. So if you happen to have an antenna and receive those signals, then you can measure travel times between a given point on the ground and the satellites that you have within your line of sight. And then you can convert this travel time into distance. And then if you know distances to more than 3 satellites, then you can get the actual position by simple geometry. So these are kinds of instruments that we use to do GPS measurements. They're not very different from the GPS navigators that you have in your cars. These antennas are slightly bigger and more accurate, and we allow them to sit at a given location for a significant amount of time to improve the accuracy. And in the end, what we're getting is this pattern of velocity vectors or displacement vectors that tell us how fast and by how much this part of the ground has moved over a given period of time. Another technique that we're using is called INSAR, or Interferometric Synthetic Aperture Radar. And it consists of a microwave instrument on board of some moving platform, such as a satellite or an aircraft, that sends pulses of electromagnetic energy down to the Earth and then records the backscatter. And the satellite is going on repeated orbits. It's providing its own source of illumination, so it does not depend on day or night condition or cloud cover. And then when we collect these images over some period of time, then we can subtract radar phase in the before acquisition and the after acquisition to form this fringe pattern, which we call radar interferogram. And fringes here really represent the amount of motion between points on the ground and the satellite antenna. So this is the actual interferogram of the El Mayor earthquake, and now I'm going to talk about the El Mayor event in some more detail. So El Mayor Cucapá earthquake was the largest earthquake to strike Southern California in about 18 years. This inset shows the regional map with the red line indicating the plate boundary between the Pacific plate and North American plate. And this is a zoom in on this area. This red star shows the epicenter of the Cucapá El Mayor earthquake, and white lines show the offsets that a team of field geologists have reported shortly after the earthquake by just going in the field and measuring them. This blue line is inferred rupture trace of the Laguna Salada earthquake that happened in this area about 120 years ago. This red line is the surface trace of the fault that we inferred based on the analysis of space geodetic data. And as you can see, it effectively doubles the rupture lengths. And this is supported by locations of aftershocks that are shown here by white dots. As you can see, aftershocks from this earthquake extend all the way from Bay of California into the Cucapá Mountains, and then they cross the international border into US territory. Our Mexican colleagues are classifying these earthquakes in the north as illegal aftershocks. Here are some pictures of the surface rupture. You can see the fault scarp. Here is a person for a scale. And these are radar interferograms that give us a fairly accurate and detailed view of how much ground has moved in the result of this earthquake. So the fault rupture is shown here by a dashed line, and every color fringe in this image corresponds to about 2.5 centimeters of motion. And as the fringe density gets larger toward the fault trace, it means that displacements get larger and also strain is increasing. And this is a map of total horizontal displacements that we can obtain from these kinds of interferograms. with displacements in centimeters shown here. So we have a generally higher displacement near the fault trace, and they then grade back to 0 far away, just like one would expect. Well, one thing that we can use with this highly detailed information on surface displacements is that we can invert it to say something about how the fault look at depth. So this is inversion for the fault structure, and you can see that slip has extended from surface down to depths of maybe 10 to 15 kilometers. And colors indicate the amount of slip. So going from 0 slip for blue color all the way to more than 3 meters of slip for red color. We can also plot aftershocks shown here by black dots to see how they relate to areas of highest slip. And it turns out, in fact, that the fault had a fairly simple trace at the surface, but a rather complex structure at depth. Here I'm rotating this so that you can see it better. And so it has this propeller-type structure. It changes dip as the rupture was propagating from the hypocenter both to the north and to the south. One interesting feature of this comparison is that, for example, we can see that aftershocks tend to hug areas of high coseismic slip. And so they're happening on the periphery of area of high slip. And that makes sense mechanically because this is the area where stress was actually increased in the result of that earthquake. One other use of these kinds of slip models is that we can put them into a model and calculate how much stress has changed in the surrounding crust. And this is an example of this type of calculation in which blue color indicates a decrease in shear stress on the potential fault plane oriented northwest. And a red color indicates an increase in shear stress in the same direction. And one thing you may notice here is that there are lots of these aftershocks to the north of the border that seem to be correlated with areas of warm color. And so the implication is that they were likely triggered by stress changes from this earthquake. Now, we can use exact same techniques that I just showed you to study slower tectonic processes that eventually give rise to earthquakes. And this is a much more challenging problem because now we have to measure signals which are much, much smaller. So we have to look at lots of data, and we have to combine them in the hope to reduce the noise. But the results that I will be showing you here next come from this area around Salton Sea. This area is centered on the southern section of San Andreas, and we hope to get some idea about how fast this fault is training at the surface and perhaps get some insights as to what's happening at depth. So this work builds on our previous study that was published a few years ago. And these are results of, these are newer data that were obtained in collaboration with Italian colleagues. And these maps show velocities of the ground. This represents slow tectonic motion. Here you can see a color scale. Essentially, we have rate of motion between what we call stable North America and Pacific plate of about 1.5 centimeter or 15 millimeters per year. So this just gives you an idea of how small a signal we can measure. These are 2 satellite tracks that cover adjacent areas, and in fact these tracks overlap in space, and so when we co-register them together, you see that we in fact measure deformation on the ground quite confidently. In addition to that, we also use data from a network of GPS stations, and we can infer not only the spatial pattern of velocities on the ground, but also the time dependence. And this shows a comparison of a time series of deformation inferred from INSAR data, shown here by black dots, and GPS time series shown here by red stars from this station SIO3, which is in fact continuously recording data not far from here. By combining these radar swaths into larger mosaics, we start seeing some interesting features. So first of all, let me point out that there is some systematics into how these colors in these maps change as we go across the plate boundary. You see that there is a zone of transition from green color to yellow color and from yellow color to red color. And not surprisingly, these transitions are associated with major crustal faults. Here we have the San Andreas fault and the San Jacinto fault, which are the 2 main players. We can combine these highly accurate line of sight maps with continuously recording GPS data to see exactly how this deformation is partitioned across the plate boundary. And next I'm going to look at the profile that goes 100 kilometers each way from the trace of San Andreas Fault, and it's about 50 kilometers wide. So what I'm going to do is that I'm going to take all the points inside this box and collapse them onto a single line to obtain a single profile. And this is what I get. Here I have a comparison between INSAR data shown by the gray dots and ground measurements, GPS and electronic distance measurements shown by these red symbols. And you can see that these independent data are in very good agreement. The next step is to really try to model these data in terms of what velocity does each fault have at depths. And so we need to understand how this total motion across the two plates is partitioned on major crustal faults in the area. And so this is a tricky exercise because often you can fit the same data using models that look different. But this is an example of one of such exercises in which we do a fairly good job in fitting the observations. And the result that we get from these observations is the so-called slip rate, or the rate of motion on major faults at depths. And for San Andreas, the current numbers are in the range of 15 to 20 millimeters per year. In fact, it's a bit lower than the previous estimates, which in fact is a good news because it means that the fault is straining at a lower rate. So seismic hazard may be just a little bit lower, but they're still large enough so that when we take this rate and multiply it by the time over which the fault did not have an earthquake, so it remained quiet, we have a number in the range of 4 to 6 meters. And that's a large number. It just gives you an idea of what's the potential for next great earthquake, how much the fault can move in order to catch up and come in equilibrium with the underlying substrate. Okay, so now I'm going to switch gears a little bit and talk about how we can use this scientific knowledge in societal interest, or how we can translate this knowledge into something that we can do to prepare for these kinds of events. This is a very good opportunity to give this lecture just before Shakeout activities that will be happening next week. How many people here know about Shakeout? Okay, there are a few of you. How many people will be actually participating in the Shakeout activities? All right, so let me say a few words about what Shakeout really represents. Originally, it started as a possible earthquake scenario based on best science. So the idea was really to take everything that we know about major faults in California and see what kind of ground shaking could result from a potential earthquake on the faults that we know about. And in this case, Southern San Andreas was chosen as the most likely candidate. In this shakeout scenario, the fault was assumed to run for 180 miles, nucleating at the south near Bombay Beach near Salton Sea, and rupturing all the way to the big band of San Andreas Fault. This magnitude of the simulated earthquake was about 7.8. The map I'm showing here on the right shows the intensity of shaking predicted by this numerical model. And the next step, the important step that needed to be taken is what this scientific prediction really mean in terms of impact on the local population and infrastructure. So I'm going to show you the simulation, the simulated motion from this shakeout rupture scenario. So here the fault nucleates at the south. Many of you may have seen this movie before. And what is shown here is the peak ground velocity in meters per second. So the rupture propagates to the north. And one feature that you may notice here is that there is this very high amplitude protracted shaking in the Los Angeles area. And that results from the fact that there is a low velocity sedimentary basin that is capturing the energy of seismic waves, just like light is captured inside the light cable. So I'm going to show a different movie that shows the same kind of simulation. Here on the left we have nucleation of rupture near Bombay Beach, and then it propagates to the north. And this is a view of ground shaking. It's highly exaggerated, but still realistic pattern of ground shaking viewed from Long Beach. And what you see here in this simulation is peak ground velocity shown by a red color. This is what we call a P wave. This is the first wave that propagates out of the source region and moves at the highest speed. Therefore, it arrives first at any given location. It really does not produce much of a shaking. Most of the shaking is associated with the trailing S wave and surface waves that arrive sometime later. And so here what you can see is this propagation and entrapment of seismic energy into the sedimentary basin, and now you see this front of strong shaking. Notice that now we're 70 seconds into simulation, so there is some delay between the rupture initiation and the arrival of the actual seismic energy. And now you can see the pattern of ground motion, how it would happen according to that particular prediction. So the ground would move both sideways and vertically, and the amplitude of that ground shaking will indeed be pretty intense. Again, for comparison, Northridge earthquake produced strong shaking that lasted about 7-15 seconds. Here we're talking about ground shaking of the order of a minute, or perhaps even larger. And that actually has important implications for the stability and integrity of high-rise building, because those buildings in fact have frequencies that are close to the frequencies of the seismic radiation. So in Northridge, duration of shaking was a critical factor. If duration lasted for longer, in fact many of the buildings would have gone down in the result of that earthquake. Let me move forward. This is a summary from the shakeout scenario for the duration of ground shaking at different locations. Here you see that we indeed are talking about tens of seconds and into the range of minutes. These are some predictions from that hypothetical earthquake in terms of the infrastructure damage, and you see that these numbers are indeed quite staggering. In fact, this is not even a worst-case scenario. First of all, this is thanks to the fact that a lot was done by state authorities to really retrofit the old buildings and retrofit the bridges, and so we have in place good building codes, and this is perhaps the first and the most important line of defense against losses from a significant earthquake. It's also not the worst case scenario because this particular scenario was kind of remote, so San Andreas is not really crossing major metropolitan areas. It's just the seismic radiation that reaches that area. And so there are possibilities in which we can have quite strong earthquakes that are sitting exactly where we have buildings and high population density. And also this scenario does not include Santa Ana winds. And according to these calculations, about half of the losses will be associated not with the ground shaking itself, but with the fires that will be following that shaking. So what about San Diego? You may have seen that from the shakeout simulation, the impact on San Diego perhaps will not be as severe as on Los Angeles. Of course, everyone will feel that and will not escape unscathed in this case, but it's really not that dramatic. But of course, we have our local earthquake hazards here in this area, and most people perhaps know about the Rose Canyon Fault that runs just offshore here. So let me mention some of the facts about Rose Canyon Fault. It's shown here by this blue trace. It goes offshore up to the north and connects with the more extensive fault system that is known as Newport-Inglewood Fault. By the way, here we're located just right off the Scripps Pier. And then Rose Canyon Fault takes a turn, which is a compressive bend in the fault, and this compressive bend is exactly the reason why we have a Soledad Mountain and elevated topography in this case. And then it continues further in the valley and just follows Highway 5. So good news about Rose Canyon Fault is that it has a fairly low slip rate. The slip rate estimated by geologic studies is about 1 millimeter per year. So it's about a factor of 10 to 20 less than more active San Jacinto and San Andreas fault. The bad news is that we don't really know what the so-called recurrence interval is, or when the last earthquake on the Rose Canyon fault has happened. So in terms of seismic hazard, both of these variables are important, because you can imagine that even if you have a very slow deformation rate, if you wait long enough, you can accumulate a significant amount of stress, and so seismic hazard is really a product of these two. So Rose Canyon itself has a potential for magnitude 6 to 7 events. These events can produce quite significant impacts, especially if you're close to the rupture. One can expect high-frequency seismic waves and high acceleration shaking. We in fact have an example of an event of magnitude 6.6 that happened a few years ago in Iran. It was a BAM earthquake. Here you have a map that shows the earthquake rupture and aftershocks, and the city of BAM, which was very unfortunately located right above that earthquake fault. And you can see here some of the aftermath. This is an old fortress before and after the earthquake. This is the fault slip model that we derived by looking at some of the satellite imagery, and you can see there is this area of high slip directly below the surface. And so the seismic energy was propagating straight up. There was no lead time. Waves were just coming from the source and hitting the ground almost instantaneously. This is the satellite radar image of the epicentral area, and you see city of BAM and Baravat as these bright reflectance locations. These bright areas are there because buildings, in fact, are very efficient reflecting surfaces, so they scatter lots of energy back toward the satellite. Here's the airport that acts more like a mirror, and therefore it appears dark in the radar image. And now this is what we call a radar coherence map. So what it means is how much the ground conditions have changed before and after the earthquake. So yellow color means little change. Blue and purple color indicates a lot of change. And so in these populated areas, in fact, most of that decorrelation came from complete collapse of buildings and complete resurfacing of the ground in the result of the earthquake. By the way, the earthquake rupture itself is right here, indicated by this streak of blue color. So what one can do to prepare for earthquakes, things are really simple, but at the same time, everyone should keep them in mind. For example, just ask yourself, at the last time when you experienced strong shaking from El Mayor earthquake or from some other earthquake, what did you do? Did you have a plan? Did you ran out of the door? Did you hid under the table? Did you just do nothing? So it's good to have a plan in advance and sometimes practice it. So these are just rules that everyone should follow, and I'm sure most people here actually do follow them. So what we have next week, on October 21st, there will be a Southern California-wide annual public earthquake drill. It will be at 10:21 a.m. In fact, it's the third time the event of this scale is occurring in Southern California. The first shakeout was carried out in 2008. It's a day of special events, really, to inspire people to get ready for big earthquakes. We have millions of participants. I think more than 6 million people now have registered to participate in Shakeout at this point. This is the first year that UCSD will be holding a campus-wide earthquake preparedness exercise. It will be on a different date, 2 days just before the actual Shakeout. But if you would like to learn more, I encourage you to visit this website and get registered. Talk to your neighbors, your family, your colleagues at work. And so the message is get involved and participate. So here I'm going to stop. Thank you very much, and I will take questions. Okay, so the question was, whether we can measure 1 millimeter per year that I mentioned for the Rose Canyon Fault with satellite measurements or space geodesy. The answer is no, it's in fact too small. It's within the errors of our measurements. So we only know that from geologic studies. So people have dug up trenches and measured the offsets and dated those offsets, and this is how we have some idea about the slip rate on the Rose Canyon Fault. Okay, so the question was what would be the effect of subsurface water, especially in Long Beach, where there was some oil extraction and then replacement of extracted oil with seawater. And the answer is that usually when we have water-saturated sediments, they do not behave well during significant shaking. So what happens is what we call a liquefaction. So water gets mobilized, and this whole stack of sediments that was behaving like a competent solid all of a sudden becomes a liquid. And all of things that are starting to happen at the surface, including sinking of various kinds of objects and really extreme motion on the ground, because the earthquake shaking gets amplified in areas of low velocity. And in fact, lots of behavior of this type was happening in the El Mayor earthquake, in the areas that were in the agricultural valley. And so there were lots of soft sediments, and there were really widespread liquefaction that really caused a lot of damage. In fact, the liquefaction was the primary culprit behind destroying essentially the entire irrigation system. So right now, agriculture in the Mexicali Valley is almost shut down, and so they're working on rebuilding the canal structure again. Okay, the question is if we can use SAR data to image what's going on below the surface. And the answer is not directly. INSAR measurements provide us with very precise motions of the Earth's surface, but in order to understand what goes on below the surface, one has to really use some kind of a model. So it's not a direct measurement, it's a model-dependent kind of inference. Okay, so the question, yes, the question was when was the last earthquake on the Rose Canyon Fault? And what was the size of that earthquake? I actually don't know very well the dating of the last earthquake. Perhaps Tom Rockwell of San Diego State is the person to ask, because he was doing the work. And the size of the earthquake is really not well constrained, because these two variables are very difficult to determine separately. So usually when geologists have a good constraint on the timing of the last event, they have a poor constraint on the amount of slip, and vice versa. All right, so the question was that some time ago in the 50s, there was some motion across a fault line in the 70s.
When they cut the road.
Right.
They saw the fault line.
Yes, so here in La Jolla, and there were some white lines drawn across the fault, presumably to measure the offset, and the answer is probably yes. So in those days, this was the main and easiest way of actually measuring offsets, just going out in the field and deploying some simple instruments. Okay, so the first question was if we have a good idea whether the rate of plate motion was different in the past compared to what we measure at present. And the answer is generally yes, because there are ways in which we can determine plate motions over timescales of tens of millions of years and hundreds of millions of years. And those involve different types of geophysical measurements. But as far as, for example, plate motion in the western US is concerned, for example, the relative motion between Pacific and North American plate, what we measure at present using geodetic data that represent averages over maybe a few years to a few tens of years are in fact in excellent agreement with geological measurements that represent averages over millions of years. So at least over those periods of time, it looked like the plate motion was pretty constant, and it was what it is now. The second question about why the plates move the way they move, why they choose particular directions. Ultimately, this is determined by what's going on in the Earth's interiors, because in the Earth's interiors we have a very slow motion, which we call convection. It's just a circulation of highly viscous, highly sluggish rocks, and it's that convection pattern that ultimately determines what happens on the Earth's surface. So plates affect the Earth's mantle convection in many ways. In fact, they may be providing significant driving force for plate convection, but it's the interaction between where plates go at the surface and what happens at depths, which really determines the present pattern of relative plate velocities and their directions. Okay, so if I understood the question correctly, it was about another plate that was located somewhere in the Pacific at greater depths. And we have no knowledge of such a plate. So everything that we know about the relative kinematics and dynamics of motion across the plate boundaries consistent with the view that we have a fairly competent and coherent North American plate and the Pacific plate, and in their interiors they're not really deforming, so they act like rigid bodies, and at depths there is no indication that there is some other chunk of material that is moving at significantly different velocity, and so they seem to behave and act like coherent units, and all of action is happening on the boundary between them. Okay, so the question was about activity in Japan and in Tokyo in particular, and whether the type of faults that they have over there are similar to ones that we have in California, and in particular San Andreas. In Japan, they have a completely different type of faults. They're called thrust faults, and they're associated with the so-called subduction zone. So what happens in Japan is that the Pacific plate is diving below Japan islands, and the relative motion between that diving plate and the overriding plate is in fact producing friction and earthquakes on this great megathrust. And so potentially the size of earthquakes in subduction zones is much, much larger than the size of earthquakes we can expect on a strike slip fault like we have in California. So in short, they have much more dangerous kind of faults than we do here. Okay, so the question was whether there is any relationship between weather and earthquakes, and I guess between climate and earthquakes, whether global warming somehow may affect the occurrence of large earthquakes. There is no definite data that we know about that would point out to the relationship between weather and earthquake occurrence. Earthquakes are nucleating down at depths of 5-10 kilometers, and so at those kinds of depths, information from the atmosphere really does not propagate deep into the Earth. Also, the types of changes that are associated with changes at the surface of the Earth are fairly small. So here we're talking about tectonic stresses that may be megapascals and tens of megapascals in magnitude, and what happens in the atmosphere produces signals or loading which is many orders of magnitude less. So there are no good physical reasons to also believe that there will be a connection. As far as global warming is concerned, again, temperature changes globally are so small, even though they have very important impact on the climate, the effect on the solid Earth is really minuscule. So short answer is no. Okay, so the question was about the earthquakes that are happening offshore and whether they have some impact on seismic hazard. What I was showing today was indeed based primarily on land data, and this is because this is where we can make these precise measurements of surface deformation. We also have very dense seismic networks that tell us quite precisely where these old little earthquakes are happening, and they seem to be associated with major faults. We can also measure the locations of earthquakes that are happening offshore, and indeed there are large significant faults that we know about that are in fact off the California coast to the west from us. One example I was showing was Newport-Inglewood fault that goes offshore in LA and continues, just parallels the coast, and then makes a landing again here in La Jolla. So these faults are important. They take up some of the relative motion between the North American and Pacific plate, but they do not slip at rates that are as high as faults inland. And we know that because we have measurements further offshore, for example, in the Catalina Islands. And so there is not much of a velocity difference between, say, La Jolla and Catalina Islands. And from that measurement, we know that there is not much of a relative motion on these deep faults offshore. But they do produce earthquakes from time to time. Yeah, the question was about the current views on the so-called triangle of life, where you should really hide when you feel strong shaking. And I think indeed this view was evolving through time. So there was a time at which it was believed that the triangle of life is important. Now I think this view is disfavored because you want to get away from the moving objects. And so if you are in a doorway, or if there's some hinging surface that can move around when the whole building is moving around, you want to be away from such objects. And so now the thinking is that you really should drop, cover, and hold under some solid surface like a table or something that you can find around. So just stay away from moving objects, and the best advice is really to go to the Shakeout website and check out the most recent information and suggestions.
Well, I want to thank you very much, Yuri. That was wonderful.